Welcome to the second part of lecture 1, which is on particle dynamics. So, if you remember the first part of this, we have derived the expression of terminal settling velocity, and we also have seen different equations of terminal settling velocity falling in different region. And if you see this equation, this is the generalized equation of terminal settling velocity, and here Vt is a function of Fd. Now, what happens when we do not know the region in which particle is falling, then I cannot take the value of Fd. For example, if I do not know whether the particle is falling is laminar region or any other region, so how I can take value of Fd? If it is falling in laminar region, then only I can take the value of Fd as 24 by Re. Now, to know the value of Fd, we should know the value of Reynolds number, and to calculate Reynolds number, again we need the value of terminal settling velocity, that is Vt. Therefore, this Fd as well as Reynolds number calculation is trial and error based. It is not directly based until unless I know the region in which particle is falling. So, to handle such situation, we have another expression of another way to calculate terminal settling velocity, and about this you can study in detail in this reference. So, in this method what we have taken, that what we have considered, that resistance force per unit projected area, the resistance force per unit projected area of the particle under terminal falling condition Rho dash, and it is given by this expression. So, Rho dash is the resistance force and resistance force per unit area, and here we have multiplied it with projected area of particle. So, Rho dash into 1 by 4 pi d square equal to 1 by 6 pi d cube rho s minus rho into g. Now, what is this right hand side expression? If you remember, where we have started derivation of terminal settling velocity. So, here this complete expression is equal to Fd, and if you match this equation with this, it is equal, because here we have dp and that dp will be replaced at the place of 1. So, when we resolve this equation, this expression, the same expression we will get, and that is equal to Fd. So, Fd basically A into K into F, and if you see the parameter Rho dash into A, so what is Rho dash is? Rho dash is nothing but the multiplication of K into F. So, same equation you can use over here, but instead of K into F we have to write the parameter Rho dash. And if you see this expression as well as this expression, some of the parameter are denoted differently. For example, here we have taken diameter of particle as d, previously we have taken this as dp, and in this case we have taken rho s, and that is the density of solid, and here we have taken density of particle rho p, and here this is the density of medium or fluid, and in this in previous expression we have represented this with rho f. So, here you can say parameters are same, but their notation are different. So, but I have already defined, so you can resemble the parameters with the previous definitions of parameters. Now, here using this particular expression we can find the expression of Rho dash, which is 2 by 3 d rho s minus rho into g. So, this is the expression of resistance force on the particle, and further we will consider this expression, and both side of this equation we can divide by rho u naught square. Here left hand side also as well as right hand side also we have divided it by rho u naught square, where u naught is nothing but the terminal settling velocity, that is Vt we have represented previously. So, if you consider this expression, further we will multiply both side of this equation by Reynolds number square. If you see this expression, that is u naught square d square rho square by mu square, this is nothing but the Reynolds number square. So, Rho dash by u naught square into Reynolds number square, it is equal to this expression into Reynolds number square. So, when we resolve this equation, and in this side if we see that u naught square and here u naught square is cancelled out, and we can further write the expression which is present to right hand side like this, 2d cube rho s minus rho into g by 3 mu square. Now, if you consider this particular set which we have encircled, that is d cube rho s minus rho into g by mu square, if you consider this expression, this we have denoted with Galileo number, that is Ga, or sometimes we also call it Archimedes number Ar. So, if you consider the Galileo number, all parameter which are available in this number are known to us. For example, if we have to calculate terminal settling velocity of a particle, I will aware with the diameter of particle, I will aware its density, mu of fluid as well as density of fluid, both parameter we will know, and g value also know. So, we can calculate Galileo number once I know the parameters, and these are usually known to us. So, if you consider this particular expression, that is Rho dash by rho u square into Reynolds number square, this we can equate with 2 by 3 into Galileo number. So, this expression is a function of all known parameters to us. So, here we have Reynolds number as well as this expression as Galileo number we can find. Further, we have this expression. So, how we can calculate terminal settling velocity using this? Once I know the parameter, I will calculate Galileo number, and 2 by 3 will be equal to this parameter. So, the value of this whole parameter can be calculated. And this table, if you see, it is having the data of log Re as a function of log R by rho u square by Reynolds number square. So, if you see, this is the same parameter which we have used over here, and log of this is equal to 2 by 3 Galileo number. So, I know already the Galileo number. So, I know the log, I know this parameter, and I can calculate log of this. So, once I calculate log of this, by referring this table we can calculate the value of log Reynolds number. For example, if log of this is coming as 2.15, so you can see here we have the value of log R dash by rho u square into Re dash square. So, here we have the value 2, and I have to find the log Reynolds number value correspond to log of this expression as 2.15. So, here we have 2 value and 0.1 is available over here. So, I will consider this particular value, and further 2.2, that is 2 is available here and 0.2 is available here. So, further I will collect this value. Now, making interpolation between these two, I will calculate the value of log Reynolds number at 2.15. So, once I know the Reynolds number, I can calculate terminal settling velocity of particle. So, instead of using trial and error method, we can use this method directly to calculate terminal settling velocity. And here Re dash, that is Reynolds number dash, is Re that we have previously defined. R dash by rho u square is a form of drag coefficient, and this value r dash by rho u square, its value is equal to fd by 2. So, by this method we can calculate terminal settling velocity of particle directly, and this is specifically used for spherical particles. So, if we have to calculate the terminal settling velocity of a spherical particle, I can calculate it directly without knowing that in which region particle is falling. So, instead of using previous laws, that is Stokes law, Newton's law, we can use this method directly to calculate the terminal settling velocity, but it is only applicable for spherical particle. If we have to calculate settling velocity of non-spherical particle, we have to follow the trial and error method. There is no other way of doing that. So, this graph is again showing the same values. Here this is basically r dash by rho u square into Re on this y axis, and x axis is basically Reynolds number dash. So, using this graph also we can calculate the terminal settling velocity. Here another graph is also plotted, but we have to use this graph for spherical particles. Now, as far as derivation of terminal settling velocity is concerned, we have taken some of the assumptions, like all 6 assumptions if you remember, which we have discussed in part 1. Now, at this point we are going to relax some of the assumptions. So, first assumption we will relax is particle is spherical. Now, we calculate, now we consider the expression when particle is non-spherical in shape. So, considering this, we will study the effect of particle shape on terminal settling velocity. So, there are two difficulties with experimental data available on drag coefficients and terminal falling velocity for non-spherical particle. The first is an infinite number of non-spherical shapes exist, and second, each of these shapes is associated with infinite number of orientation which the particle is free to take up in a fluid, and the orientation may oscillate during the course of settling. So, for example, when we consider irregular particle, sometimes it will fall like this, sometime it may fall like this, sometime it may fall like this, and sometime it may fall vertically also. So, orientation is continuously changing when the particle is falling in a fluid. So, that is another difficulty. So, in recent study it was found that most satisfactory characteristic linear dimension to consider the shape is sphericity. If you remember, this sphericity we have discussed in the first week of this course, which is basically the surface area of particle divided by surface area of a sphere of equal volume. And the limitation of this whole approach is that if we calculate the terminal settling velocity using given equation, and if we carry out experimentation for non-spherical particle, so error used to come about 16% and maximum error may be of the order of 100%. So, to reduce this error, separate shape factors in Stokes as well as Newton's law region are considered. So, you can see the effect of shape will be considered by considering another factor in Stokes as well as Newton's law. Now, another problem in such condition is that while settling, non-spherical particle will not travel vertically in fixed orientation. As we have discussed that continuously orientation is keep on changing when particle is falling in a liquid. In general, the resistance force to movement in gravitational field will not act vertically and particle will tend to spiral and to rotate. Therefore, if particle is non-spherical, then volumetric diameter of particle is considered in place of dp. What is volumetric dia? I guess you remember this, it is the diameter of a spherical particle of same volume as the particle. Therefore, to consider the non-spherical shape of particle, we consider dV instead of dP in all equation, and along with this we will also consider phi s, that is a sphericity of the particle, to incorporate different shapes. Therefore, Reynolds number for irregular particle or non-spherical particle is defined as dV Vt rho f by mu f. Previously we have taken this as dP, now we will take diameter as dV. So, for non-spherical particle, the Fd and Reynolds number Rep can be plotted using log graph, which we have seen previously also. So, same axis we will use for that is log axis to plot Fd and Reynolds number for non-spherical particle, and a separate curve is obtained for each shape of the particle and for each orientation. For example, if you see this graph, what this graph shows, you see the bottommost line we have discussed previously also, and this is for spherical particle where psi is equal to 1. So, psi is keep on changing when we move upward, and we have different lines to calculate Fd based on Reynolds number, and all these psi will depend on different shape. So, you see here we have Fd versus Reynolds number plot for different value of psi s. For Stokes law, here we have the expression of terminal settling velocity. Up to here we have already seen in the previous part of this lecture. Now, this expression is multiplied by another parameter, that is k1, where k1 is defined as 0.843 log psi s by 0.065. So, psi s is basically considering the shape of particle, and here we have taken volumetric dia of particle instead of dP. So, this is the revised expression for Stokes law when the particle is irregular and it is falling in laminar zone. Similarly, we can change the parameter for Newton's law also. Here you see this is 4 by 3 into rho p minus rho f by rho f into g dV divided by C2 and power 1 by 2. So, this C2 is basically the correction factor when we are studying the effect of shape on terminal settling velocity. So, this C2 is defined as 5.31 minus 4.88 psi s. So, considering K1 in Stokes law and C2 in Newton's law, we can study the effect of particle shape on settling velocity. And again here we have considered all this assumptions. In this up to here we have already relaxed the first assumption. Now we are going to relax sixth assumption, that is the fluid forms an infinite medium. So, previously we have assumed that fluid is falling and infinite medium, it means it is falling in a cylinder filled with the liquid. So, that cylinder diameter is significantly large in comparison to the diameter of particle, and therefore, the movement of particle will not be affected by the wall of the cylinder present near to us. Now, we are relaxing this assumption to study the effect of wall on terminal settling velocity. So, the boundaries of the vessel containing the fluid in which particle is settling will affect its settling velocity. If the ratio of diameter of the particle dP to that of the tube capital D, where D is the inner diameter of cylinder or tube, is significant, if the ratio of diameter of particle dP to that of D capital D is significant, the motion of particle is retarded. Now, why it is retarded? It has two different effects. First, as particle moves downward, it displaces an equal amount of or equal volume of liquid which must rise through the annular region between particle and the wall. And second is the velocity profile in the fluid is affected by the presence of tube boundary. So, these are the two effects when particle is falling in a smaller diameter cylinder or tube. So, the effect is difficult to quantify accurately because the particle will not normally follow a precisely uniform vertical path through the fluid. Therefore, if the fluid is bounded with a confined space, that is a cylinder, the upward velocity of displaced liquid will be higher, which increases the resistance to fall the particle and therefore decreases its settling velocity. Now, why it happens? Why when volume goes, when the particle displaces the volume of liquid of its own volume, then it exerts the resistance, and why the settling velocity is decreased? Because the projected area of particle reduces the effective cross sectional area of the container. For example, initially I am having the container of this diameter, and if particle is moving like this. So, when particle is moving like this, it displaces the liquid, and if you see, this is the diameter of cylinder and this is the diameter of particle. So, effective area of the cylinder through which liquid will move will reduce. So, it will reduce the effective flow area of displaced liquid, and as a result velocity increases. So, once velocity will increase, the resistance on the particle will increase, and that is why the settling velocity of particle will decrease. So, the effect of walls on the dynamics of particle thus depends on the geometry of the vessel, and therefore a generalized correlation is difficult to propose. And experimentally we can rely on the correlation for laminar settling of a spherical particle. The correlation is Cf, which is equal to 1 minus dp over capital D and whole raised to the power 2.25. So, this is the correlation to count wall effect when the particle is falling in laminar zone, and similarly this expression we are having to account the effect of wall on particle movement when the particle is falling in turbulent zone. So, once I know the value of Cf, then I can calculate the revised settling velocity of particle, which is equal to Vt into Cf. So, Vt, you remember, this is the settling velocity which we have derived in first part of this lecture, and Cf we have just seen. So, multiplication of these two will speak about the actual settling velocity of the particle considering the effect of wall. So, and when we have to consider irregular particle, we can replace dP with dV, that is volumetric dia. So, in this way we can study the effect of wall. Further, we have 6 assumptions, in which 2 we have already relaxed. Now, here we are going to relax another assumption, that is particle is freely settling under gravity. What is the meaning of this? That previously we have assumed that no other particle is available to put hindrance in the path of single particle. So, single particle movement or dynamics we have discussed. Now, here we are considering the number of particles, because in usual condition we deal with the mixture of particles or number of particles, not a single particle. So, when there is a mixture of particles or when it is concentrated suspension, the individual particles tends to interfere with each other's dynamics, and therefore the velocity of motion or rate of settling of each individual particle will be considerably less than that for the free settling condition. So, that is the obvious situation then when we are dealing with the number of particle, the settling velocity of each particle will be decreased in comparison to when they are falling freely. So, Stokes transitional and Newton settling expression, which we have derived in part 1 of this lecture, describe the behavior of single spherical particle in an infinite fluid, and that is why we call it free settling. However, these models have limitations in practical applications. Alternate considerations such as interaction of particle in a fluid can modify the settling behavior. Therefore, settling that has these forces in appreciable magnitude, we call it hindered settling. So, when the particle is falling with the presence of other particle, we call it as hindered settling instead of free settling. So, in this slide we have shown one interesting example of hindered settling, and hindered settling is what occurs when particles are crowded and surrounded particles interfere with the motion of individual particle. So, Here up till now we have discussed in terms of number of particles. Now the same is applicable when we are discussing the movement of cars on road. Now what happens when we usually come home from the offices, almost at same time all offices are closed, so we used to have jam on the road. So the road has the capacity to accumulate 5,000 cars, and at that time we are having 4,000 cars on road. So instead of free movement, we used to move very slowly on the road, and that is the perfect example of hindered settling, which we usually see in our daily life. So the hindered settling is while the motion of large particles gets hindered, the small particle tend to get dragged down by large one and thus gets accelerated. What is the meaning of this statement? That when a number of particles are falling in a cylinder, then what happens? Some small particle, if I am considering its settling velocity, would be significantly less in comparison to large particle, as terminal settling velocity expression, if you remember, it is directly proportional to the diameter. So, a small particle will move very slow in comparison to large particle. Now, during hindered settling, what happens when I am having the small particle, and when very large particle is falling above this, then the small particle will not fall with its own velocity, it will fall with the velocity of large particle, and therefore the small particle is dragged down and gets accelerated. So this type of situation also occur while hindered settling. Each particle is in fact settling through a suspension of other particles in the fluid rather than through a simple liquid itself. So the particle is falling through the suspension, not in a clear liquid. And in that case, the effective density and viscosity of concentrated suspension, that is rho b and mu b, which we commonly called as bulk density or bulk viscosity, are much larger than those of the clear liquid. So when we are deriving the expression of hindered settling, we can consider rho b and mu b instead of rho f and mu f. So settling medium therefore offers higher resistance to the motion of particle, and thus the particle gets retarded. So here the hindered settling velocity that we have denoted with Vh of a particle is difficult to predict. Some approximation we can do by replacing rho f and mu f by rho b and mu b. So first of all we have to define what is rho b and what is mu b. Rho b is basically the bulk density, which we can define as rho s into 1 minus epsilon plus rho f into epsilon. So epsilon is the volume fraction of liquid in the suspension. So 1 minus epsilon is basically volume fraction of solid in the suspension. So that is rho s into volume fraction of solid plus rho f into volume fraction of liquid. So in this way we can define rho b, and we can define bulk viscosity, that is mu b, using this expression. And if you remember the expression of terminal settling velocity, this is the same expression, but we have written it for Vh, that is hindered settling. Why? Because here rho f and mu f is replaced by rho b and mu b, and here when we write the expression of rho b and mu b over here, further we can replace the expression in terms of rho f and mu f, and one additional term will appear. This additional term is basically represented as Fs. So hindered settling velocity would be terminal settling velocity into Fs. Fs is the settling factor, which is a ratio of hindered settling velocity to terminal or free settling velocity. So in this way we can calculate hindered settling velocity. If you see, this is a plot of Fs versus epsilon. As epsilon will increase, the Fs value will increase, and that is very obvious. Like when we have increment in epsilon, that is when we have more volume fraction of liquid, we will have less volume fraction of solid. it means solid is available in less quantity. Therefore, the particle will fall freely. So, when we increase epsilon, it will increase Fs, and Fs is multiplied with the Vt, and we can have the expression, we can have the value of Vh. Therefore, epsilon increment will give Fs increment, and then terminal settling velocity or hindered settling velocity basically will increase. So, that is all about this. Now, here we have the summary of this lecture. In this lecture, the particle dynamics is defined considering single particle, generalized expression of terminal settling velocity is derived. Now, based on different regions of Fd versus Reynolds number plot, different expressions of settling velocities are defined. Effects of shape, wall and other particles on terminal settling velocity are discussed. So, that is all about lecture 1, and here we have the reference. Thank you. Solid is available in less quantity.